If you took all the ozone floating, high up in the stratosphere and you just squished it down to the surface of the Earth, it would form a shell only a few millimeters thick.
Right, which is just, it's incredibly thin.
Yeah, it's like a layer of gas about as thin as a smartphone screen. And that is literally the only thing standing between us and total planetary devastation.
It really puts it in perspective.
It really does. So welcome to today's deep dive. We are sorting through this totally fascinating stack of sources today, including the standout excerpt titled "Amid All the Environmental Problems That Feel Overwhelming."
Oh yeah, that one is great.
It is. And our mission today is to uncover how humanity nearly destroyed that fragile shield we just talked about. And I mean, more importantly, how we actually managed to save it.
Which is such an important story to tell right now.
Exactly. If you ever feel just completely bombarded by environmental gloom, this deep dive is your antidote.
It is, because, it is incredibly rare to find a genuine, honest-to-goodness, happy ending when it comes to global planetary crises.
Right. We just don't get those very often.
No, we really don't. We're so used to feeling paralyzed by the sheer scale of our problems, right? Like assuming that coordinated global action is just, I don't know, a pipe dream.
Yeah, totally.
But the story hidden in these sources today proves that when we actually choose to, we are entirely capable of pulling off the impossible.
And that is exactly our mission today.
Yeah.
We're going to unpack the story of the ozone layer. I mean, it's a word that floats around in the background of the news a lot, but we are going to slow things way down today.
Yeah, really dig into it.
Right. We want to understand the actual science of what this stuff is, how we managed to accidentally just tear a huge hole in it, and why this specific story is the ultimate proof that coordinated global action is not just some fantasy.
And to really appreciate the scale of what humanity achieved here, we first have to understand the environment we are actually talking about.
Okay, let's do it.
Because the ozone layer is not something you interact with directly down here. It exists in a region of the atmosphere called the stratosphere.
Right, let's set the scene for the listener. So if you look straight up, roughly 10 to 50 kilometers above your head, that's where you hit the stratospheric layer.
Exactly.
It's high above the weather we experience, the rain and clouds, and it's high above the cruising altitude of commercial airplanes.
Yeah, the word stratosphere basically refers to this highly stratified, layered region of the sky.
Okay.
And it is completely, utterly calm up there. It's incredibly cold and very, very dry.
Just a vast empty space.
Right. And scattered throughout that vast empty space is a very thin, highly reactive gas, which is ozone.
And our sources break down the chemistry of this gas so beautifully for a non-science audience.
Okay.
Let's look at ordinary oxygen first, right? The stuff you and I are breathing right now just to stay alive.
The good stuff.
Yeah. That ordinary oxygen is a tightly bonded pair. It's basically two oxygen atoms locked together holding hands.
Right.
But ozone is its slightly unusual, highly unstable cousin. It forces 3 oxygen atoms into a bond instead of 2.
And that third atom makes literally all the difference.
Really, just one extra atom.
Just one. It turns the molecule into a very fragile, very reactive form of oxygen. And what is so striking when you review the atmospheric data in our sources is just how sparse it actually is up there.
Yeah, that blew my mind.
I mean, despite being spread across 40 kilometers of vertical space, there is remarkably little of it.
Which brings us back to that visual from the beginning, right? Gathering it all up and compressing it down to the surface, and it yields a shell just a few millimeters thick.
Barely anything at all.
It's like wrapping the entire globe in a single, incredibly flimsy layer of plastic wrap.
Exactly. A flimsy layer that performs a function absolutely vital for every living thing on this planet.
Okay, so let's talk about that function.
Well, it acts as the Earth's sunscreen, basically. It's up there absorbing ultraviolet radiation pouring out of the sun.
And we hear about UV radiation mostly in the context of, going to the pharmacy and buying actual sunscreen. But what is it doing on a biological level if it hits us?
So ultraviolet is a high-energy, invisible form of light. And because it carries so much energy, it doesn't just, warm you up like visible sunlight does.
Right, it's not just heat.
No, it acts as a highly destructive force right at the cellular level. When unfiltered UV light hits living tissue, it physically damages the DNA inside your cells.
Oh, wow. So a sunburn is just the visible surface symptom of that cellular damage?
Yeah, and that's just the mildest symptom, honestly.
Really?
Yeah, I mean, in larger unfiltered doses, this radiation is the primary driver of skin cancers. It causes severe eye problems like cataracts.
So human health would just plummet?
Absolutely.
Yeah.
And the damage extends way beyond humans, too. It stunts the growth of plants, which severely reduces agricultural yield.
Oh, so our food supply,
Yeah. And crucially, it damages phytoplankton.
which are those tiny microscopic organisms in the ocean, right?
Right, they are at the very base of the ocean food chain.
Huh.
If those marine organisms die off from severe radiation exposure, the entire global food web basically collapses.
So without this little millimeter-thick layer of ozone soaking up the worst of those rays and only letting, a survivable amount through, life on land would just be battered by radiation.
Battered to the point of being entirely uninhabitable.
That is terrifying.
It is, and the sources highlight a really profound evolutionary milestone here,
Oh,
actually.
yeah, the history of it.
Yeah, so billions of years ago, before the ozone layer even formed, life on Earth could only survive by hiding deep underwater.
Right, because they couldn't handle the sun.
Exactly. The ocean itself acted as a physical shield against the solar radiation. It wasn't until oxygen slowly built up in our early atmosphere and eventually reacted to form that protective layer of ozone that it actually became safe enough for organisms to crawl out of the oceans and onto land.
That is just wild to think about. Our ancestors only made it onto the beach because this weird three-atom oxygen cousin just happened to set up a protective barrier in the sky.
Yep. It is an absolutely foundational precondition for our existence.
So, having established that we literally owe our existence to this fragile, incredibly thin shield, how in the world did we manage to accidentally dismantle it in the span of a single human lifetime?
Yeah. It's quite the plot twist.
I mean, it wasn't malice, right? It was tied to an invention, from what I read.
Right. It was tied to a family of chemicals called chlorofluorocarbons.
Okay, that's a mouthful.
It is. So to save our sanity, we will just use the acronym from the sources and call them CFCs.
Thank you. Because, wait, I need to stop you here for a second, because everything I've read in these sources paints a picture that is just deeply ironic.
How so?
Well, on paper, CFCs were considered an absolute chemical miracle. I mean, they were cheap to produce, they were entirely non-toxic to humans, they were non-flammable.
Perfect. Exactly.
Right. You could literally breathe them in without getting sick. So why would something so incredibly safe to handle down here in our kitchens become the ultimate villain up there?
Well, to understand the celebration around CFCs, you kind of have to look at what they were actually replacing.
Okay, what came before them?
So, before the 1920s, refrigerators used gases like ammonia or sulfur dioxide to keep things cool.
Which doesn't sound safe at all.
It wasn't. If your vintage refrigerator sprang a leak in your kitchen back then, those toxic gases could literally kill your entire family in their sleep.
Oh my gosh.
Yeah, it happened frequently. The industry desperately needed a safe alternative.
Ah, so they were actually trying to solve a very real deadly problem down here on Earth.
And they succeeded brilliantly, to be fair. CFCs were engineered to be perfectly stable.
Okay.
They didn't react with anything, they didn't catch fire, and they didn't poison anyone. They were so successful that we just put them in everything.
Right, they became the cooling gas in all our refrigerators and our air conditioners.
Exactly.
They were the propellant spraying our aerosol hairspray cans and deodorants. They puffed up foam packaging. They were just everywhere.
But the sources explain that the very trait that made them a miracle in the kitchen.
Their stability.
Exactly. Their extreme chemical stability.
Yeah.
That is exactly what caused the catastrophe in the atmosphere.
Because they couldn't be destroyed.
Right. Most industrial chemicals, when they escape into the air, they break down relatively quickly. They react with other elements in the lower atmosphere, or they just dissolve in water and get washed out by the rain.
But CFCs were different.
Very different. They were specifically designed not to react.
Mm-hmm.
So when a refrigerator leaked or, a can of hairspray was emptied, those invisible CFC molecules just drifted out the window, completely intact.
And because they never broke down, they just kept drifting.
Slowly and silently, year after year.
Just rising higher and higher into the atmosphere.
Yep, ascending for years until they finally breached the stratosphere.
And the stratosphere, as we covered, is a radically different environment than the surface.
Oh, completely. Up there, high above the clouds, there is literally nothing shielding the chemicals from the full, unfiltered power of the sun.
The very ultraviolet light that the ozone layer is trying to absorb in the first place.
Exactly. So the UV radiation hits this indestructible CFC molecule. And the energy up there is so intense that it finally shatters the chemical bond.
It breaks it apart.
It does.
Yep.
And when that CFC molecule shatters, it knocks loose a single, highly reactive atom of chlorine.
And this is where the real disaster starts.
Right.
Because this invisible microscopic disaster happening miles above our heads, it revolves around a specific chemical mechanism.
The catalyst.
Yes, the sources describe the freed chlorine acting as a catalyst. And let's try to visualize that for you listening because it's a bit abstract.
It's a great analogy.
So imagine a bowling alley. Normally, when you roll a bowling ball, it crashes into the pins, it transfers its energy, and it loses momentum. It stops.
Right, standard physics.
Right. But a catalyst in chemistry is like a magic bowling ball that never loses momentum.
I love this visual.
It flies down the lane, obliterates a pin, which in this scenario is an ozone molecule, right?
Exactly.
And then it bounces off completely intact and immediately flies into another pin. And another.
Yeah.
And another. It just doesn't stop.
That is a perfect visualization of how a catalyst functions. It drives a chemical reaction without being consumed by it.
It just keeps going.
Yeah, so the chlorine atom physically rips the three-atom ozone molecule apart, right? It bonds with one of the oxygen atoms and leaves normal oxygen behind.
Okay.
But then a subsequent reaction frees that chlorine atom up again.
So it's loose again.
Exactly.
Uh-huh.
It emerges from the destruction completely unharmed, reloaded, and ready to attack the next ozone molecule.
That is horrifying. And the math laid out in the text is just staggering.
It really is.
It says one single freed chlorine atom can wreck tens of thousands of ozone molecules before it naturally cycles out of the stratosphere.
Tens of thousands.
Tens of thousands of protective molecules destroyed by a single atom.
Picture the global scale of this for a second. For decades, a slow, continuous trickle of this seemingly harmless, stable gas from our daily conveniences was just rising into the sky.
From every house on Earth, basically.
Yeah. And once it crossed into the stratosphere, the sun just transformed it into an unstoppable army of ozone-destroying agents.
It's literally an invisible battle in the sky.
That's exactly what it was.
But eventually, this invisible battle produced a very terrifying and highly visible consequence down on Earth, right?
Fast forward to the 1980s.
Right. So in the 80s, scientists were taking these routine measurements of the atmosphere over Antarctica.
Just normal science stuff.
Exactly. They fully expected the data to look normal, just a standard atmospheric profile.
But it wasn't.
Not at all. The readings showed that ozone levels over the South Pole were crashing dramatically every single spring.
Crashing to a degree that was almost unbelievable, from what I understand.
Yeah, the thinning of the protective layer was so severe, and it covered such a vast region that it became known as the ozone hole.
A massive, gaping vulnerability in our planetary shield.
I mean, just imagine standing in that research station in the 1980s. You look at the data coming out of your instruments, and it's basically telling you that a massive chunk of the atmosphere is simply missing.
The shock was so profound that the scientists from the British Antarctic Survey actually doubted their own findings at first.
Wait, really? They didn't believe it?
No. The drop in ozone was so incredibly steep that they just assumed their sensors were malfunctioning.
Oh, wow.
Yeah, they literally thought their equipment was broken.
Because they just couldn't believe humanity was capable of doing that much damage that quickly.
Right, it was unprecedented.
But wait, I have a question about this. Why Antarctica?
Yeah.
Because nobody is down at the South Pole spraying hairspray or, running millions of window AC units.
No, definitely not. It all comes down to a lethal combination of isolated weather and extreme chemistry.
Okay, explain that.
Well, during the long, completely dark Antarctic winter, the temperature drops so intensely low that something highly unusual happens in the stratosphere. Clouds form.
Wait, clouds in the stratosphere. We just established earlier that the stratosphere is completely dry and empty.
Usually it is. But in the extreme, like minus 80-degree cold of the polar winter, the microscopic amount of moisture up there actually freezes into what are called polar stratospheric clouds.
Okay.
They're these strange, iridescent ice clouds. And those tiny ice crystals are the crucial missing piece of the puzzle here.
How so?
They provide a physical, solid surface for the chemical reactions to take place.
Oh, I see. So instead of two gases just randomly bumping into each other in the empty sky, the ice acts like a workbench.
Exactly. The chlorine compounds rest on these ice crystals, which accelerates their destructive power exponentially.
That makes so much sense.
Yeah. And furthermore, the weather patterns over Antarctica create a massive swirling phenomenon called a polar vortex.
Which traps it all.
Right. It acts like a giant atmospheric wall, trapping all that supercharged cold air and chlorine in one place. It essentially creates a perfect, inescapable isolation chamber, where the chlorine can just feast on the ozone uninterrupted throughout the spring.
Wow. So the data just forced humanity to confront undeniable evidence that everyday industrial chemicals, the literal stuff keeping our groceries cold, were rapidly tearing a hole in the Earth's life support system.
It was a genuine planet-scale emergency.
Right, because if that thinning continued and spread globally, the consequences for human health and agriculture would have been catastrophic.
Absolutely. So, faced with this terrifying reality, humanity had to make a choice. We had to figure out how to navigate a global crisis where the cause was deeply, deeply embedded in modern life.
Which brings us to the twist in our story.
The good news.
Yeah, the good news. Because in a surprising turn of events for an environmental narrative, the world actually did the right thing here.
They really did. They listened to the science, the data was clear, the mechanism was proven, and the international community realized they simply could not afford to wait.
This brings us to 1987, right? The Montreal Protocol.
Yes. Nations from all over the world convened to draft a treaty committing to phase out the production of CFCs and all related ozone-depleting chemicals.
And we really need to pause and highlight just how unprecedented this treaty was.
It honestly cannot be overstated. The Montreal Protocol became the first treaty in the entire history of the United Nations to achieve truly universal ratification.
Every single country.
Every single recognized country on Earth, despite vast geopolitical differences and economic disparities, they all eventually signed on.
That is just incredible. The entire globe agreed on a single course of action.
They did, and the chemical industry, which, initially pushed back.
As they do.
Right, as they do. But they eventually found substitute chemicals. They developed alternative refrigerants and propellants that could cool our fridges and spray our aerosols without breaking down in the stratosphere and wrecking the ozone.
So they just swapped it out.
Exactly. The production of CFCs was systematically wound down, and then it was stopped entirely.
So humanity identified a global threat, agreed on the scientific cause, collectively changed its industrial behavior, and it worked.
The policy was a massive success. The world pivoted. However, we do have to introduce some vital nuance here, echoing the careful tone of our sources.
Okay, lay it on me.
The treaty was a triumph of diplomacy, yes, but chemical reactions in the sky do not care about ink on a page in a UN assembly hall.
Right. We stopped manufacturing the villain, but what is the actual reality of the healing process today? Like, is the hole gone?
Well, the sources warn strongly against overstating the current good news.
Right.
The ozone layer is healing, yes, but it is a painfully slow process.
Is that because of that very chemical stability we talked about earlier?
Precisely. CFCs are incredibly stubborn. They linger for decades.
Wow.
Because they take so long to cycle out of the atmosphere. The chemicals that were released by our parents and grandparents back in the 70s and 80s are actually still up there.
You're kidding. They're still up there doing damage right now.
They are. They are still drifting through the stratosphere, still getting shattered by ultraviolet light, still releasing chlorine, and still destroying ozone today.
So the destruction didn't just instantly halt the day the treaty was signed?
Not at all. In fact, the Antarctic ozone hole still opens up every single spring, driven by that same polar vortex and those same ice clouds, just as it did when it was first discovered.
But it is getting better, right?
Yes. The good news is that the data shows the hole is gradually shrinking over time. It is unequivocally on the mend. But complete recovery, like getting the stratospheric ozone back to its healthy pre-1980s baseline, that will take until somewhere around the middle of this century.
Okay, so we are looking at a timeline measured in decades, not years.
Exactly. It serves as a very sobering lesson about the sheer momentum of planetary systems. Environmental damage takes a very, very long time to undo, even long after the human activity causing the harm has completely ceased.
That is a stark reminder.
It really is.
But even acknowledging that slow timeline, the big picture takeaway from these sources is truly marvelous.
It's incredibly hopeful.
Because we were faced with an invisible threat high in the sky. It was a problem no single country could fix alone, right? Like, if the United States stopped using CFCs but Europe and Asia didn't, the hole would just keep growing.
Yep, it wouldn't have mattered.
But instead of throwing up their hands or getting bogged down in endless debate or denying the science entirely, the world actually cooperated.
Which is exactly why the Montreal Protocol is so frequently brought up when we talk about the most pressing global challenge we face today.
Climate change.
Climate change.
Yeah. The parallel is so obvious there.
It is. But following the strict caveats in our source material, we do have to be honest about the differences here.
Right.
Because as much as we might want to just say, we fix the ozone layer so we can easily fix global warming, the sources point out a massive hurdle.
What's the hurdle?
Fossil fuels are woven far, far more deeply into the foundation of the global economy than spray can propellants ever were.
That makes sense.
Asking the entire world to transition off coal, oil, and gas is a much heavier lift than asking chemical companies to just change the refrigerant inside a kitchen appliance.
Right, because you're talking about the energy that powers entire civilizations versus, like, a chemical used for cooling and foam.
Exactly. It represents a completely different scale of economic reliance.
Yeah.
But that difference doesn't invalidate the historical lesson here.
Definitely not.
The story of the ozone layer proves that when we understand a danger clearly and we choose global cooperation over isolation, we are genuinely capable of protecting the thin, fragile systems that keep this planet livable.
We did it once. That thin, millimeter-equivalent shield overhead, slowly stitching itself back together, is the literal proof that humanity can course correct.
It is the ultimate evidence that planetary scale unity is, in fact, possible.
It really is. And as we wrap up this deep dive, there is a final thought worth mulling over for everyone listening. Think back to the sheer relief of how the ozone crisis was actually solved.
Right.
The secret to saving the stratosphere wasn't that everyone on Earth had to suddenly give up their refrigerators or, sacrifice modern cooling.
Right. Nobody had to unplug their AC unit.
No. The solution was a technological swap. We universally agreed to substitute harmful chemicals with safe alternatives, allowing society to just keep functioning normally behind the scenes.
A massive, invisible substitution that saved the world without requiring a radical change in daily human behavior.
Exactly. So if we look at our current environmental crises, what is the modern equivalent of that universal swap?
That is the big question.
Can we apply this exact same blueprint to climate change? Can we simply swap out dirty energy grids for clean ones behind the scenes, allowing you to just live your life basically unaware of the change?
Right.
Or does our deep, tangled reliance on fossil fuels require an entirely different kind of human cooperation, one that demands a fundamental shift in how we actually live, consume, and behave?
It is a massive question.
It's a profound question to consider the next time you step outside, look up, and think about that invisible shield protecting us all.